Thank you very much, Mr. Chairman. And I would like to start by thanking the organizers for this opportunity to address this forum. And I will be representing somehow the electrochemistry community here. It's big shoes to fill. But what I wanted to talk to you today is small objects actually trying to deal with the biggest problems in humankind, which is energy. So it's a big challenge, and the electrochemists, since the Enlightenment, actually have been looking at how to store energy. And that's, we have a very interesting talk just preceding my presentation, which give you a view in the German market, which I thought it was extraordinary, very interesting. But we are actually interested also to look globally. So here are the energy or power demand growth rates. And I don't need to discuss in this forum what is driving this energy increase. This has been discussed extensively. What I want to actually just point out in this graph are these scales. So we're talking about here that by 2050, we're going to be needing an excess of a 10 terawatt power. And that's globally. So how can we meet that power demand without compromising the environment? And the key issue here is CO2 emissions. So we actually turn to renewables. So if you look at the renewables, and these numbers, of course, the details can be discussed, and there is a devil is in the detail. But we just look at the global numbers, so the potential power that you can draw from different renewables. As you can see, these are very important energy that can be tapped. They can be tapped locally. We heard today about the possibilities in Scotland in terms of hydroelectric and onshore wind. These are very important solutions, and this has to be implemented, and this has to be definitely invested in. But when we look at globally, there is only one superpower, and that is solar. So what we need to actually look here is at this amount of power here, and if those of you that were eagle-eyed looking at the presentation early this morning will find that the actual power available from solar energy is half of that, which is correct. That's the power that you will have available at the sea level. This is impinging the planet, but that dwarfs all the other energy sources. And you've looked today at the possibilities of nuclear and looking at the energy potentials and the nuclear fuel capacity. We are still way orders of magnitude below what solar energy can produce. So the real challenge, as far as we are concerned in terms of energy storage, is how to make solar energy and renewables in general work and energy production for society. So this is my nanoeconomics slide from the electrochemical point of view. So essentially, our argument is that the only way that we can make renewable energy a primary energy source is by storing and locking that energy in chemical compounds. That means to generate fuels. And the previous speaker talked about one of those options. What I just highlight here are two different energy vectors that we've been investigating. This generation of hydrogen from water, and there is some very important aspects that I just want to briefly highlight. And the other one is the conversion of CO2 to liquid fuels. And I just want to highlight today the challenges involved in both approaches. These are not new ideas, but the demand at the moment for clean energy have brought them back forward with a vengeance. So our argument here is that when we produce these energy vectors, then this could be used to power fuel cells, another very important element in the energy production, particularly locally, I would say. But this can actually work on demand. And that gives a power density that is comparable to combustion engines. Therefore, it could be used in-house and replace battery technology, as we discussed earlier, that represent a challenge. So this is our main argument. This is the only idea that I want you to take with you today. That's the main message of my talk. So if I look at, first of all, water splitting, just to refresh you from some chemistry arguments. So there's a negative charge here. It doesn't appear on the screen. But essentially what we have is a material that absorbs energy, so promoting an electron into a higher energy level. And that the main argument here is that that electron is capable of reduced protons to hydrogen. This is the main field we want. And also generate oxygen from water. As you can see, both reactions involve more than one electron, and the transfer of protons. So in terms of device fabrication, at a very fundamental level, we are dealing here with very difficult chemical reactions to be addressed. And this is where this area in particular, when you have many electrons involved, is where require materials with very, very specific properties. Another important aspect here is that energy gap, which has to match the solar energy. So if you take into account the energy difference between these two reactions here is approximately 1.23 electron volts, thermodynamically speaking, but because they are so energetically demanded, we require an extra energy to actually drive those reactions. And this is more or less the state of the art. As you can see here, there's a number of oxides that show efficiency for direct conversion of photon to field above 10%. But all of these materials, well, some of them here, for instance, this cadmium sulfide, they're not stable, they're not suitable for this type of applications, and all of them are absorbing light way in the UV. That means the region of the solar spectrum that is very weak at sea level. So there are new developments that are working more in the visible range. This is the important one, the one we want to target. However, the efficiencies are very low. And there are ways that we can boost these efficiencies by creating what we call tandem cells, where we can actually combine photovoltaic with solar power water splitting in a configuration that resemble actually natural photosynthesis. In that case, trying to target this region here, and this is the main challenge in this area. So there is very wide research carried out in different parts of the world to actually challenge this, to achieve this goal. The other vector that I mentioned earlier is the conversion of CO2. Again, you won't be able to see those numbers there, but here what we have is this pie chart that also been discussed early throughout this forum. Essentially, the emission of greenhouse gases per area, per different areas of energy generation. And you can see here energy supply, transport, and residential have very important contribution. This is in the UK. In the US has a similar distribution. So our argument here is that if we want to convert CO2 into efficient material, efficient fuels, this has to actually operate in these applications there. So there is very little argument, we believe, to transform CO2 for the construction industry. So we want to actually generate CO2, and that, we want to process CO2 to fuels that can be used in this application. In particular, transportation, I think there is an achievable target. So if we look at this simple energy distribution here, this is the chemical view of energy worldwide. So we have CO2 right up there. This is the least energy. This is the more energetic. There are a series of energy jumps from going from this set of chemicals. These are liquid. This is gas. This is gas. And what we would like here is either use renewable energy to store it, actually by taking CO2 and transform it to this set of chemicals here rather than all the way to gas, because all of this can be used as fuels. Alternatively, we can use renewable energy to catalyze. So this is not storage, but catalysis in a way to transform methane to fuels again. And these are ways that we can actually generate a variety of these fuels that can power fuel cells. Now, what are the challenges here? To actually kickstart the reduction of CO2, you need to inject an electron into that molecule. So you got to go to that step there, and that's extremely energetic. So CO2 is a very stable molecule, and you need a very efficient catalyst to actually deal with this reaction. Once you manage to do that from the electrochemical point of view, from the chemical point of view, then all hell breaks loose. So you have all of this reaction that can take place, and the problem there is selectivity. We don't want to generate a wide range of molecules that then need to be separated in a very complicated process. We want to be selective to particular type of products. And we have been investigating these processes by looking at very small particles, and with the idea to actually create systems that are selective. So these are particles that are approximately 20 nanometers, and then that goes into a carbon matrix that has to be well dispersed. This has to go to essentially form mesoporous layer, where you can actually have the interaction between the gas, the electrolyte solution where you create the fuels, and the electrons. And all that has to go into laboratory test cells, and the idea is that within that distribution here, we can actually obtain a promising catalyst that can go to units like this one demonstrated by DMV, where we can actually match solar energy to CO2 conversion into formic acid. So this here represents more or less a TRL unit, and I fully recognize that what I have been speaking so far is at the bottom of the food chain in technology readiness level, but this is the way we see that we can actually store terawatts of energy. Incidentally, you have seen through the slides some institution here, and these are greatly acknowledged by their support and believe in these ideas and our partners. So what is the key guiding principle? And I'll finish with this slide. The key guiding principle that we are developing in terms of catalyst is abundance of materials. And this is something that is also very close to another discipline that we're working very intensely, which is photovoltaic materials, sustainable active layers for photovoltaic. And as you can see here, there is a logarithmic scale of the price of extraction in dollars per kilogram. So here we have $0.01, so 10 cents per kilo, to $100,000 per kilo. And here there's a distribution of elements, and we've done very interesting fundamental work, for instance, in gold-palladium system, but gold-palladium system are sitting right here. So these are not catalysts that we can actually exploit to large quantities of devices. So what we need is to actually draw a line, and what we have arbitrarily draw a line around the $50 per kilogram. So these now are the elements that we are actually focusing on, in particular elements, materials involving copper and zinc, tin as well, iron. These are the materials or the raw elements that will allow us to really expand this system into a real terawatt or gigawatt energy. So solar poses a really fundamental challenge, and renewables in general, and that's the storage. And we would like to deal with that with this sort of technologies that allow us to generate solar energy with sustainable materials and at the same time store it as chemicals. And once you can store a chemical, then we can actually deal with the distribution in different scales. Something that electrochemistry has demonstrated in the past is the scalability. So electrochemistry is a very important discipline in the area of microelectronics to create integrated circuits, and it's also a fundamental technology in the car industry. So you see it goes to different scales. So this is the concluding remarks that I want to bring, and just to also bring to your attention the fact that we are closely engaged with the Cabot Institute at Bristol University, which actually deal with global problems. And Bristol is actually setting a very ambitious target, and is recently unveiled last week, plan to install 1 gigawatt of solar energy by 2020. And this is in conjunction with the sort of being named European Green Capital in 2015. So there are challenges, but also there is a drive and ambition to achieve those. And if I'd just like to finish with the thought that today we've looked at attempts to bring renewables and the challenges. We have listened earlier an attempt to estimate the environmental cost, a particular point that I thought it was missing in the discussion yesterday. And when we talk about renewables as only viable because there are government subsidies, I would like to bring the point that this is the view when you don't take into account environmental costs. And environmental costs is the big subsidy that you and I, by month-old daughter and the next generation will be paying. Thank you for your attention.